Okay, so let's start today's lecture. Okay, so today we are going to continue with our discussion on second order equations. Okay, so but we will be talking about a very important new type of second order ordinary differential equation that will be called Euler's equations. Okay, so we'll be considering Euler's equations. Okay, so the Euler's equation. So what is an Euler's equation? An Euler's equation is in general the non-homogeneous Euler's equation is going to take the form. Okay, so it's going to take the form x squared y double prime plus alpha x of y prime plus beta of y is equal to g of x. Okay, so that's a non-homogeneous Euler's equation, and the corresponding homogeneous one is x squared y prime plus alpha x of y prime plus beta of y is equal to 0. So that's the homogeneous equation. Okay, so that's the Euler's equation. So let us look at the Euler's equation more carefully. Okay, so let us look at the Euler's equation more carefully. Okay, so if you look at the Euler's equation more carefully, you're going to see. Okay, so you're going to see that we're looking for the function y is equal to y of x, right? So you're looking for a function y is equal to y of x, and since y is a function of x, x is the variable, y is the function. Okay, so however, the point here is that this is not constant coefficient, right? So but rather the coefficient here is actually polynomials in x, right? So that what happened here is that if you have a second derivative in y, then x has to be squared, so that the number of powers of x agrees with the numbers of derivatives of y. And same thing here. So this is y first derivative. This is actually to the power of 1. Is that good, family? This is the zeroth derivative, right? So so therefore there's no x here, x to the power of 0. Is a good family. Okay, so the Euler's equation is like it's a linear equation, right? So if we just test it on your exam, this is a linear equation, right? So that you can classify it as linear, but it is a linear equation with variable coefficients. The coefficients are not constants, but they are functions of the variables, right? So and they are functions of the variables in the sense that the powers. Okay, so the powers of x agrees with the number of derivatives in y. So that's kind of an you have to be able to identify an Euler's equation by yourself. Okay, so be able. Okay, so let's say let me be clear. Okay, so you have to be able. Okay, so be able to identify an Euler's equation by yourself. Okay, so as you have seen on the exams, sometimes they on the exams you're not going to be told that which method you should use in order to solve a certain problem, right? So it's hard to say that, but in general you have to be able. Okay, so you have to be able to identify the use of an equation by yourself. Okay, so that's kind of the very important thing. Okay, so for example, t squared y double prime plus alpha of t of y prime plus beta of y is equal to 0 is also an Euler's equation, right? So that's like just the x is now replaced by t. Okay, so that's kind of the same. So now with all this at hand, okay, so with all this at hand, we're going to discuss the solutions of the homogeneous Euler's equations. So a homogeneous Euler's equation as something like this. So x squared y double prime plus alpha of x of y prime plus beta of y is equal to 0, right? So that's like a homogeneous Euler's equations. Okay, so and how do you solve them? How do you solve them? Well, the idea here is that you can see that we have been if it was like a constant coefficient equation, we were trying the solution y of x is equal to e to the power of r of x, something like this, right? So, but you can immediately see that this type of solution won't fit the Euler. Why? Because if you take derivatives, then you're going to see y prime of x is equal to r times e power of rx, y double prime of x is r squared e power of rx, but then you're going to have polynomial powers of x, so that x squared is multiplied by here. This is x. So in the end, you won't end up with 0, but rather a polynomial of x. So that's not a good method. Okay, so this is not a good method. So what particular solutions we should specifically try? Well, we should try a function of the form x absolute value. Okay, so let me say, for example, let's not suppose x is just positive. Okay, so let's say x is positive. Then you're going to see that x to the power of r, right? So y prime of x is r x to the power r minus 1, r multiplied by r minus 1, x to the power r minus 2. Why is that good? Because then the number of derivatives matches I mean, each time you take a derivative, you're going to lose a power of x, and it's compensated by the power of x multiplied here. So that means that, so that means x prime y x squared y double prime plus alpha x of y prime plus beta of y is equal to x squared multiplied by r minus 1 multiplied by x r minus 2 plus alpha of x of r x to the power r minus 1 plus beta of x to the power of r. So that in the end, you get r multiplied by r minus 1. Okay, so plus alpha r plus beta. Okay, so multiplied by x to the power of r. And you want to set this to be equal to 0, which means that this is just, this one has to be 0. So that in the end, so finally, right, so finally, you're going to see that r squared plus alpha minus 1 of r plus beta is equal to 0. So that's a new kind of the idea is like the philosophical idea is like similar to what you have before, but here the methodology is completely different, right? So what happens here is that it is very important to notice here that you are working with an Euler's equation that's not constant coefficient, but the powers of x should agree with the number of derivatives in 1. So that's the point. And you would like to try a function that's not exponential, but a power function. So x to the power of r with the power r is going to be determined. Okay, so now after you take derivatives, you find a nice thing is that if you take the power function as your sample, as your solution, then the x squared is going to be multiplied by the power r minus 2. X is going to be multiplied by the power r minus 1, and you have x. So that x to the power of r will be a common factor. And if you decompose this common factor out, you're going to have a quadratic polynomial. And you set the quadratic polynomial to 0. This is the new characteristic equation. So we will say that this is the characteristic for Euler, right? So that's a characteristic equation for Euler type. So if you look at the characteristic equation for Euler, first thing that in terms of Euler's equation, besides x squared, the coefficient here is 1, right? So you have just alpha and a beta. But however, you won't, if it was classical constant coefficient equation, you will have like r squared plus alpha r plus beta. But here you won't have that. You will have alpha minus 1 instead of alpha. So you have to subtract the 1 from this alpha. You get something like this. So that's finally what happens to the characteristic equation for Euler. Okay, so that's kind of the thing. And now if you have this characteristic equation at hand, same as before, you're going to have R1 and R2. If both of them are real and they're distinct, right? So that's the case that they're real and distinct. Then the two solutions are like y1 of x is x to the power of r1, y2 of x is equal to x to the power of r2, and the general solution y of x is c1 x to the power of r1 plus c2 x to the power of r2. So that's kind of the general idea, right? So, but what happens if you have a double root, or if you have like complex roots? So that's kind of the problem, right? So So that's kind of a problem. But here I would like to remind you that, for example, if R1 is not equal to R2, it is easy. Okay, so it will be easy to check that the Y1, Y2, they're going to be fundamental solutions. Okay, so that means that the Wronskian, we've been talking just about it, right? So x to the power of R1 and x to the power of R2. You calculate the Wronskian as x to the power of R1, x to the power of R2, right? So R1 x to the power of R1 minus 1 and R2 x to the power of R2 minus 1. So that's going to be just the R2 minus R1 multiplied by x to the power of R1 plus R2 minus 1. This is not going to be 0 if R1 is not equal to R2. So that's kind of, you have a fundamental set of solutions just to check. Okay, so that's in this form. But we have not really settled the case when R1 is R2 is a double root or maybe complex roots. So in general, okay, so general theory for homogeneous Euler equations. Okay, so there is a general theory for homogeneous Euler equations that you must memorize throughout this lecture. Okay, so what's the general theory for homogeneous Euler equation? So one should start from recognizing this homogeneous Euler equation: x double prime x squared y double prime plus alpha x of y prime plus beta of y double prime is equal to 0. Sorry, beta of y. Okay, so beta of y is equal to 0, right? So that's kind of the Euler's equation. Now, first, you should start with the characteristic equation. Okay, so the characteristic equation is going to take the form r squared plus alpha minus 1 of r plus beta is equal to 0. So that's the characteristic equation. You solve the characteristic equation. Okay, so you solve the characteristic equation. So that's going to give you R12 is minus alpha minus 1 plus minus square root of alpha minus 1 squared minus 4 times beta divided by 2, right? So that's kind of the two solutions. And then you have to discuss, right? So you have to discuss different cases, right? So you have to discuss the different cases that you might lead to different solutions. Okay, so different cases that might lead to different solutions. So what are these cases? Well, the case one. Okay, so there are actually several cases. Okay, so the case one says that you have two real roots and they are distinct, right? So that's case one. Okay, so case one is real distinct roots. So that means R1 and R2 are both real and they are not equal to each other. Okay, so if you have this case. Now, if you have this case, then you are going to have a solution, right? So the solution, okay, so solution is going to take the following form. Okay, so let me, maybe I will cut this piece. Okay, so we'll cut it. Okay, so. Okay, so maybe I will cut it. Okay, so. Right, so the solution theory is going to take the following form. Okay, so so let's. Okay, so okay, so that's the general theory for our homogeneous Euler equation. Okay, so that's. So with this general theory at hand, we can start to talk about the solutions when you have real distinct roots. So the solution is y1 of x is actually equal to x to the power of r1, and y2 of x is equal to x to the power of r2. So here, instead of just the x, we're taking actual value of x in case that x is negative. So you have to remember that in general, for Euler's equation, the x is replaced by absolute value of x. Okay, so that's that will be general solution. And therefore, the solution in general will be C1. Okay, so C1 x to the power of R1 plus C2 x to the power of R2. So that's going to be the solution. Okay, so that's case one. Now, what about case two? Okay, so case two is going to be real a real double root, right? So let's say case 2 is the say real repeated root case. So let me do a complex root case first. Okay, so that's case 2 is going to be complex conjugate roots. Okay, so case 2 is complex conjugate. Right, so they are complex conjugate roots, and the complex conjugate roots can be written as lambda plus minus I times mu, with a common real part and common complex part. So that's like what we did before. But then you're going to have the solution. That's something that you really have to memorize. Okay, so the solution is going to take the form C1 x to the power of lambda. So again, the real part, it's like what we did before. The real part has to enter the exponential. But here the exponential is actually replaced by the exponent in the power. So because you are using power functions, you're not going to have exponential, but you're going to have x to the some power. And the complex part, again, is going to enter sine and cosine. But when it enters sine and cosine, it is going to enter the sine cosine with a logarithm factor. So that what happened here is that the solution y of x is c1 x to the power of lambda multiplied by cosine. Okay, so mu logarithm of x plus c2 x to the power of lambda of sine of mu logarithm of x. So this is what you have to really memorize. And it's not very hard to memorize. Remember, real part and enters the exponential. It's just exponential is replaced by the polynomial power. And the complex part enters sine and cosine. And when it enters sine and cosine, the mu is sine and cosine. But you're not going to be sine mu x or cosine mu x. It's going to be sine mu multiplied by the logarithm of x and cosine mu multiplied by the logarithm of x. Okay, so that's kind of the case where you have complex conjugate roots. Okay, so now let's start. The third case is the double root case. Double real root. Okay, so double real root. So that means R1 is equal to R2 is equal to R. So suppose you have this case. Then there's also a form of this solution. It's going to be y of x. We are going to see that in this solution, we're going to kind of previously it was a golden principle saying that you have an exponential function, then you have an exponential function multiplied by t or x, right? So here you're not going to multiply by x, you're going to multiply by logarithm of x. So situation is very similar to here. You're not going to really use x, you're going to use logarithm of x. So that's going to be the same. So c1 x to the power of r plus c2 x to the power of r, but you're going to multiply by the logarithm of x. Is that good, family? Okay, so that's kind of the sin. Okay, so the golden principle is now replaced by a multiplication towards logarithm of x. Okay, so that's the new golden principle that we are facing in this scenario. Okay, so that's a kind of general theory for homogeneous Euler's equation, how you're going to find a set of fundamental solutions. Okay, so I will leave to you, it's a nice exercise to check that these two solutions as well as these two solutions, they're really fundamental solutions, right? So that means the Wronski is now 0. Here I have to remind you that in general, the x is replaced by the absolute value of x. Okay, so that's kind of in case when x might be negative. Okay, so but in general, x is supposed to x is positive. We don't really need that absolute value. You can just use x. But if x is negative, then you really it will really be useful to consider the negative x by absolute value. Okay, so here let me show you an example. Okay. And the important thing, okay, so just one more remark is that you must memorize that the characteristic equation is not alpha, but alpha minus 1. You have to subtract the 1 from that alpha. Is that good? Okay, so let me show you an example. Okay, so here's a nice example saying that can you find the general solution of this equation? This equation is x squared y double prime. Okay, so plus 7 times, okay, so plus 7 times x of y prime. Plus 13, okay, so plus 13 times y is equal to 0, okay, so it's equal to 0. If you have that equation, then you can see that, so on an exam, your standard steps in solving this equation is to first start with the characteristic, right? So let's say you first start with the characteristic equation, so that's going to be r squared plus 7 times r plus 13 is equal to 0. Am I right or wrong? Anybody has idea? Anyone can correct me? Anything? Remember, this 7, this alpha has to be replaced by alpha minus 1. That's very important, right? So that's kind of the error is made here, right? So that's kind of so that's thing you must remember is that alpha in Euler's equation, when you look at for the characteristic equation in Euler, you cannot use alpha, you must use alpha minus 1. Alpha minus 1 is a good family, okay? So once you have that, you can solve for the roots. So R12 is minus 6 plus minus the square root of b squared, so that's 36 minus 4 times 13 is equal to 52, right? So and divided by 2 times a, so that's kind of minus the plus minus minus of the 16 divided by 2, so that's kind of minus 3 plus minus 4, so that's I. Is a good family, right? So 16 2i, okay? So that's going to be a solution, R12. So that means lambda is equal to minus 3 and mu is equal to 2. Some people say, can I take mu as minus 2? This is the same rationale as what you see before. If you replace mu by minus mu, you're just going to flip the C1 and C2. I mean, it doesn't quite matter. So I can take mu equal to 2. So the general solution, okay, so when you write down the general solution, you must memorize the formula. So that's important, okay? So you must say that the general solution is C1 x absolute value to the power of lambda, so minus 3, and then it will be cosine and sine, right? So it will be cosine and sine. So then you are going to see that this is cosinuses of mu logarithm of x, right? So and plus C2 x to the power of minus 3 multiplied by sine 2 logarithm of x. So that's going to be the way how you find your solutions. Okay, so that's going to be the way how you find solutions. Okay, so let me show you one more example. Okay, so this example says that can you find a general solution? Here I replace the x by t, right? So that's everything is now replaced by t, right? So this one says that we are going to have t squared y double prime. Okay, so t squared y double prime minus 2t of y prime plus, okay, so plus 3 times y is equal to 0, right? So, but t is positive, so you don't really need the absolute values, right? So t is your x before, and it is positive, okay? So that you can have the characteristic equation is r squared minus, so 2 should be minus 2 should be minus 1 and more, so that's 3 times r plus 3 is equal to 0. You solve for the r, so r12 is minus b plus minus b squared is 9 minus 4ac, right? So it's 12 divided by 2a, so that's kind of 3 over 2 plus minus square root of 3 over 2 times I. You're going to have this is your characteristic rules, right? So once you have the characteristic rules, you're going to have the solution. So I mean, if you are very familiar with this, you don't have to work with lambda and mu. You can just say that y of t. Okay, so y of t, you can just write the solution immediately by yourself. Okay, so y of t is c1 t to the power 3 over 2. All right, so t to the power lambda, right? So and then is cosinuses of mu is square root of 3 over 2 logarithm of t, and then plus c2 t to the power of 3 over 2 of sine square root of 3 over 2 ln of t. So that's going to be the way how you find your solutions. Okay, so that's going to be the way how you find your solution. So this is how people work out an Euler's equation. Okay, so an Euler's equation in practice. Okay, so important thing here for you to get well on your exams is that you must memorize this summary sheet. Okay, so this is a summary sheet how Euler's equation, homogeneous Euler, so it must be homogeneous, important. Okay, so how homogeneous Euler's equation solutions are going to output from the characteristic equation as well as the characteristic roots. So that's going to be very important. Okay, so that's going to be important. Now let us consider non-homogeneous equations. Okay, so let us consider non-homogeneous equations. Okay, so let us consider now. So previously, our equations are homogeneous, but if it is non-homogeneous, it's like x squared y double prime plus alpha of x of y prime plus beta of y. Suppose it's non-homogeneous, it must be equal to some g of x. So that's going to be a non-homogeneous equation. How are we going to find the solutions for a non-homogeneous Euler's equation? So that's going to be important. Previously, we were using these characteristics. It's kind of helping us to solve the homogeneous Euler's equations. Okay, so it's kind of helping us to solve the homogeneous Euler's equations. So the point here is that how do we solve the non-homogeneous Euler's equations from this picture? Okay, so important thing is that this is a non-homogeneous linear equation. So by our general theory, we should start with the complementary equation. Okay, so right, so let's say you should start with the complementary equation, which is x squared yc double prime plus alpha of x of yc prime plus beta of yc is equal to 0. As long as you have the complementary equation, you can see of yc of x is c1 y1 of x plus c2 y2 of x. Remember, this is homogeneous, right? So this is homogeneous. As long as it is homogeneous, you can use the theory by homogeneous equations to solve this the equation, right? So that's kind of y1 and y2 can be determined by your previous theory regarding this y1, y2. Remember, for example, this is y1, this is y2, this is y1, this is y2, or maybe this is y1, this is y2. Is a good family, right? So that's kind of an easy way to find this y1, y2. So as long as you have this y1, y2, you just want to find one particular solution, right? So find a particular solution. So the particular solution, capital Y of x, right? So you want to find a particular solution, capital Y of x, that satisfies the non-homogeneous equation. How do you find this particular solution that satisfies the non-homogeneous equation? Well, we can use this method of variation of constants, right? So that means u1 of x of y1 of x plus u2 of x multiplied by y2 of x. So that's kind of the standard variation of constants method, right? So that's a standard variation of constant method that we've been just talking about before. Is that good, everybody? Right? So, and once you have both the complementary solution as well as the particular solution, you sum them, that's going to be your general solution. Is that good, everybody? So the important thing is that the variation of constants, it was an idea that there are some constants and you vary those constants into functions. You preserve the y1 and y2. So that's the key point. Is that good, family? Okay. How do you find the u1, u2? Well, remember variation of constants. So the variation, okay, so variation of parameters method, right? So, right. So the variation of parameters method is going to give you two solutions. Okay, so it's going to give you two solutions, right? So two solutions that are of the following form. Okay, so that are of the following form. So we're going to say that u1 of x is equal to integral, right? So minus y2 multiplied by the g divided by Wronskian of y1, y2. So that's a very general formula. And u2 of x is the same thing. So you integrate y1 and g divided by the Wronskian over y1 and y2. So that's kind of going to be your variation of parameters formula. Is that good for everybody? Okay. So, and is there any mistake here? Okay, so is there any mistake here? Well, you must be clear that when we talk about variation of parameters, right? So for example, in that lecture, when we were talking about variation of parameters, one very important thing, okay, so one very important thing for the variation of parameters is that you must use the standard form. So this is not an equation in standard form, right? So that's, remember, equation in standard form means that the leading coefficient in front of the second derivative should be equal to 1. So this is not equal to 1. So non-standard form, non-standard form. So the equation is actually not in a standard form. So that's a problem, right? So then you cannot really use this g as the same right-hand side in your original Euler's equation, because this is not the standard form of this equation. Is that good, family? Right? So you have to really turn this equation into standard forms. So that's going to be super important. Okay, so that's going to be super important. So that means that you have to turn this equation in standard form. Okay, so you have to turn this equation in standard form. And if you turn in standard form, so that means x squared y double prime plus alpha x of y prime plus beta of y is equal to g of x should be turned into the standard form y double prime plus alpha over x of y prime plus beta over x squared of y is equal to g of x divided by x squared. So that's going to be in standard form. So this g of x, let's say denoted by the new g tilde of x, is going to be the right-hand side that you will be working with. Is that good, family? As long as you have this, you can see that u1 of x is actually the integral of minus y2 multiplied by g tilde divided by the Wronskian of y1, y2. And u2 of x is the integral of plus y1 multiplied by g tilde divided by Wronskian of y1, y2. So that's going to be the way how you find your solutions. So that you are not going to use the g as the original Euler's equation, but you have to divide the g by x squared, right? So that's very important. And you set this to be your new g tilde, and using that, you create your set of fundamental, you set your set of variation of parameters and create a particular solution. Is a good family? Okay, so that's going to be very important. You must memorize that if you start from a non-homogeneous Euler's equation, you have to use the characteristic equation. You can use the Euler equation theory. The alpha and the beta are used. You build the characteristic equation, and as we said before, you build the two fundamental solutions. But as long as you have the fundamental solution, you want to build a particular solution, then you want to use variation of parameter method. But this g has to be replaced by the g tilde, which is the g in the standard form. So you have to turn the equation in standard form before you are able to use any of those theories about the g's. Is that good, family? Okay, so that's going to be very important. Okay, so that's going to be very important for non-homogeneous Euler's equations. Okay, so let's look at a few examples and see if we can really solve it by ourselves. Okay, so here is a nice example that I take from one of previous year's exams. Okay, so let's try to work it out before we close this section. Okay, so here's the initial value problem. Okay, so that's the problem is to find initial value problem. Okay, so this is an initial value problem. Initial value problem, t squared y double prime. Okay, t squared y double prime minus 2t. Okay, so of y prime plus, okay, so plus 2 times y. Okay, so is equal to 3 times t squared, where the y1 is 0, y prime 1 is 4. Okay, so y1 is 0 and y prime of 1 is equal to 4, suppose. Okay, so now you want to solve this equation. This is a non-homogeneous Euler. So you should start with the complementary equation, right? So we should start with the complementary equation is actually t squared yc double prime minus 2t times yc prime plus 2 times yc is equal to 0. So that's the complementary equation. As long as you have the complementary equation, you have the characteristic equation is that 2 is 2 minus, so that's r squared minus 3 times r plus 2 is equal to 0. Remember, alpha is replaced by alpha minus 1. So you're going to have this. As long as you have the characteristic equation, you solve for it. So that's 3 plus minus the square root of 9 minus the 4. Okay, so 9 minus, sorry, so here is 9 minus, okay, so 4ac, right? So so that's going to be 4 multiplied by 2. Okay, so divided by 2 times a. So that's going to be 3 plus minus the 8, so 1 divided by 2. So that's going to give you that R1 is equal to 2 and R2 is equal to 1. So that's going to be the two fundamental characteristic rules. Okay, so as long as you have these two characteristic rules, you can have your solution. Okay, so you can have your solution. Okay, so you can have your solution that so that means the homogeneous. Okay, so the general solution. Okay, so let me say the general solution to homogeneous equation. Okay, so the general solution to homogeneous equation is y of t is the C1 t to the t to the power of 2 plus C2 t to the power of 1. Is that going family? Okay, so that's going to be your general solution to this homogeneous equation. Okay, so x to the power of r. Now, with this general solution in hand, you must stick to your own choice of y1 and y2. So that's going to be very important. Okay, so you must stick to your own choice of the y1 and y2 in order to proceed. Okay, so that means you're going to say this is my y1. Okay, so and this is going to be my y2. Okay, so that's going to be, you have to stick to your own choice of this y1 and y2 before you really can proceed. Okay, so that's y1, y2. I mean, some people is going to say, maybe I choose this as y2, this as y1. It's completely fine. But you have to stick. Okay, so important thing is that if you have already made up your mind, which one is y1, which one is y2, then you have to stick to your own choice. You're never able to change it. Is that good, family? Okay, so you have this y1, y2. As long as you have this y1, y2, you're going to see that particular solution, right? So let's say particular solution. Okay, so particular solution is just going to be capital Y of t is equal to, okay, so any questions? Any questions? 3R, B2R. Okay, so let me see. Okay, so yeah, so that's a good idea. It's a very good idea. I have been emphasizing many times that this alpha, this is the alpha. Alpha has to be what? Alpha has to be replaced by alpha minus 1. I emphasized many times in this lecture. It was alpha. Okay, so it was alpha in the original homogeneous Euler equation, but when you do the characteristic equation, alpha has to be replaced by alpha minus 1. So it is good to you raise this question, right? So you have to replace the alpha by alpha minus 1. So it's like what happens here, right? So this is the alpha. This is actually the alpha, and we are going to replace it by alpha minus 1. So it's actually minus 3 times r instead of minus 2 times r. So this is a very important question, and it is nice to you raise it. Okay, so and so that's a good idea. If you have questions, please raise it. Okay, so alpha must be replaced by alpha minus 1. Okay, so alpha must be replaced by alpha minus 1. So that's going to be very important. Okay, so that's going to be very important. Just one moment. Okay, so just one moment. Okay, so just one moment. Okay. Okay, so so that's kind of the thing, right? So this is very important, right? So it's good that you raise this question, but it is very important you realize that the alpha has to be replaced by alpha minus 1. Okay, so that's kind of the thing. So let's come back. Okay, so that means the yt is u1 of t multiplied by your y1. So let me say that y1 is just t squared, plus the u2 of t multiplied by the y2 is just your t. So how do you find u1, u2? Well, you're going to say that u1 of t is equal to the integral of minus y2, right? So multiplied by the right-hand side divided by the Wronskian of y1, y2, and u2 of t, right? So it is going to be equal to y1 multiplied by the right-hand side divided by y1, y2, right? So the Wronskian between y1 and y2. However, the point here is that the g going to be this one, right? So is this going to be your g of t? Well, this is going to be not going to be the case, right? So this is not going to be the case because you must remember that you need to turn the equation in standard form. So this I have emphasized a lot here, that you must turn your equation in a standard form. Okay, so you must turn your equation in standard form. So that means you have to turn the equation in standard form, right? So you must turn your equation in standard form. So that means y double prime minus, okay, so minus this 2t, okay, so it's actually 2 over t of y prime, right? So, and then plus 2 over t square of y should be equal to what? Should be equal to 3. The t square has to be divided by t square. It is 3. So that's going to be your g of t is actually, the g of t is actually 3, right? So because you have to turn the equation in standard form. So with that at hand, you also have to calculate the Wronskian, right? So, but the Wronskian is very easy to calculate. Remember, y1 is t squared, y2 is t. So that's t squared and t. So that's 2t and 1. So that's t squared minus 2t squared. So minus the t squared, right? So that's going to be t squared minus 2t squared. So that's minus the t squared. So that's the Wronskian. So with all this at hand, you can calculate u1 of t is equal to the integral of minus of y2, right? So y2 is equal to t, right? So minus of t multiplied by g is 3 divided by the Wronskian is minus of t squared. So that's actually t over t squared. So that's the integral of 3 over t. So that's the 3 times logarithm of t. Is that good, family? Okay, 3 times logarithm of t. Some people is going to ask, why don't you use the absolute value of t? Right? So why do you just use t? Remember, here it is an initial value problem. Initial value problem means that the initial values is 1. So that means that the t has to start from 1. So therefore, you know that t is greater or equal than 1. So that's going to be important. Okay, so you already know that t is going to be greater or equal than 1. So the u1 t is already solved. And the u2 of t is the same thing. So the integral of y2 of t, right? So the y2 is given by t, right? So, minus y2. So this is plus y1, right? So plus y1 is going to be t squared multiplied by the Wronskian is 3 divided by the minus t squared. The right-hand side is 3. So that's actually the integral of minus 3. So that's minus 3 times t. So that's going to be your u1t and your u2t. Okay, so as long as you have the u1t and u2t, you know that the particular solution, capital Y of t, is going to be just the u1t is minus 3t. So that's minus 3t. Okay, so multiply. Okay, so sorry. So that's u2t. Okay, so that's going to be your u1t, right? So the u1t is a 3 times logarithm of t. Okay, so u1t is 3 times logarithm of t multiplied by t squared, right? So multiply by t squared plus u2t multiplied by t is u2t is minus 3t. So that's kind of minus 3t multiplied by t, 3t squared. Is that good, family? Okay, so that's going to be the way how you find your particular solution here. Okay, so that's how you find your particular solution. As long as you have this particular solution, so the general solution, right? So then you know that the general solution to non-homogeneous equation. Okay, so general solution to the non-homogeneous equation is actually given by y of t is equal to the complementary solution plus the particular solution. Okay, so as long as you have the complementary solution is already found, right? C1t squared plus C2t, so C1t squared plus C2t, and then plus the particular solution is 3 times the logarithm of t multiplied by t squared minus the 3 times of the t squared. Is that good, family? Right? So that's going to be how you find those solutions. And as long as you have these solutions, you can see that you can find your particular solution. However, before I do that, let me say that you have C1 minus 3. So that's a C1 minus 3 multiplied by t squared plus C2 multiplied by t plus 3 times the logarithm of t multiplied by t squared. C1 minus 3 is another constant. So then you can actually say it's C1t squared plus C2t plus 3 times the logarithm of t multiplied by t squared. That's going to be your solution. I mean, you can replace the C1 minus 3 by another C1 as your new constant. Is that good, family? Okay, but this is not enough. You can see that you want to also find particular solution. So y1 is 0, y prime 1 is 4. So y1 is 0 and y prime of 1 is equal to this 4, right? So you have to make use of these initial conditions. And if you use these initial conditions, you get a system of equations. So if you set y t equal to 1, so that's c1 plus c2 plus t equal to 1, logarithm of t 0, so you have nothing here. And this is going to be, okay, so this is going to be equal to 0, so c1 plus c2. And you have y prime of 1, so y prime of 1 is actually equal to what? Is equal to 2c1 multiplied by t is equal to 1, right? So plus the c2 multiplied by t derivative is c2. And then here, you have to take a derivative, right? So that's going to be, so 3t squared is going to be taken a derivative multiplied by logarithm of t. So that's going to be 6 times t multiplied by ln t, where t is equal to 1, plus 3 times t squared multiplied by ln t derivative is 1 over t. Again, t is equal to 1. So you can see that when t is equal to 1, this is nothing, right? So when t is equal to 1, this is actually equal to 3. So that's going to be equal to 4. So in the end, you get this relation between C1 and C2. C1 plus C2 is equal to 0, right? C1 plus C2 is equal to 0, right? So, and again, you're going to also have the relation that 2C1 plus C2 is equal to 1, okay? So 2C1 plus C2 is equal to 1. So it's easy to see that C1 is equal to 1, C2 is equal to minus 1. It's a good family, okay? Some people is going to ask, well, it looks like on your here, C1 plus C2 is 3, but that's because we didn't change the C1 by C1 minus 3. Remember, we have absorbed the C2, right? So we have absorbed the C2 by 3 and made it into a new C2. Is a good family? Okay, so that's from here, you can solve, okay? So you can solve, okay? So you can solve for this C1 and the C2s, okay? So you can solve for this C1 C2s, okay? So just make sure that I didn't have any mistake here, okay? So here, but it's completely fine, okay? So that's, yeah, so you're going to have this, okay? So that's going to be your situation, okay? 1 minus 1. So in the end, you reach a general solution, okay? So that means the particular solution, okay? So our particular solution that's going to satisfy the boundary conditions, I mean the initial conditions, is going to be given by C1 is equal to 1. Okay, C1 is equal to 1. So that's T is equal to T squared minus T, right? So C1 is equal to 1. C2 is equal to minus 1 plus 3 times logarithm of T multiplied by T squared. So that's going to be your final solution. Okay, so that's going to be your final solution. T squared minus T plus 3 ln T multiplied by T squared. So that's going to be your particular solution. Is a good family? Okay, so this is the whole process that how you solve such a homogeneous, okay, so non-homogeneous equation with a particular initial values. Okay, so that's a very nice example that you must distill and absorb after these lectures. So here I have listed quite a few exercises. They're all about Euler's equations, different types of Euler's equations, and ask you to solve them. Okay, so you must practice after the lectures and get yourself familiar with this method of Euler's equations. Okay, so that's what I want to say for today's lecture. Okay, so let's stop here and we will come back to our lecture next time. Okay, so see you next time.